Today we'll be finishing Chapter 2, or 1.2, by considering question 10, which reads, suppose that phi from f to g is a mapping from a field f to a field g that preserves algebraic operations in the sense that phi of a plus b is equal to phi of a plus phi of b, and phi of ab is equal to phi of a, phi of b for all a, b, and f. Our goal is to show four things, namely that phi of a minus b is equal to phi of a minus phi of b for all of a, b, and f. Show that phi of 0 with respect to the field f is equal to 0 with respect to the field g. Show that either phi of a is equal to 0 with respect to g for all a and f, or phi of a does not equal phi of b whenever a, b are in f and a does not equal b. Finally, we'll show that if phi of a does not equal 0 for some element a in f, then the image of phi is a subfield of g. Take a couple seconds to try this out for yourself. Then we'll give you some hints. Then we'll go on with the proof. So for some hints, for 1, try to do an additional construction in some way. For 2, try to use the results of 1. For 3, try to make it so that you follow a few steps and then you get a branching point so you can get the or and you can prove both. And finally for 4, try to recall what you'll need to prove that you have a subfield. Recall that a subfield is a subset that is also a field. And see which parts of this proof help with that already. Alrighty then, let's begin. So for question 1, we're going to do construction in the following way. Namely, we're going to want to prove that we're going to want to work on this a minus b term. And let's start by considering phi of a minus b plus b. And this is, since f is a field, this can be associative, so we can think about this in two ways. It's either we can either group these two together, and we'll just have phi of a down here, and those are equal. Phi of a, equality there. Or we can leave the a minus b together, and we can split this up using the property that it respects addition. So we get phi of a minus b plus phi of b. And then we'll recall that our definition of subtraction is namely adding the inverse. So this is phi of a plus minus b. So we can consider this phi of a plus phi of minus b plus phi of b. And we have equality the whole way through, so we can apply cancellation in the field. So we get phi of a and phi of a cancel, and we're left with 0 is equal to phi of minus b plus phi of b. But that means that phi of minus b is equal to minus phi of b. So we have that. Next, we'll go back to our thing we wanted to prove originally. So we have that phi of minus b is equal to minus phi of b. And we can apply that here in the sense that phi of a minus b, same as phi of a plus the additive inverse of b, or phi of a plus minus b. And we can split that according to our rule. So we get that the left-hand side is equal to phi of a plus phi of minus b. And then we've proven that phi of minus b is minus phi of b. So we get phi of a minus phi of b. And we're done. And we proved what we wanted. Now for 2, let's simply use our previous result from 1, and let's consider phi of a minus a. In one sense, this is just phi of 0 with respect to the field f. In another sense, we apply our result from 1, and we get this is phi of a minus phi of a. These are two elements in G, so an element minus itself is going to be equal to 0 with respect to that element G, and we're done. We have phi of 0 with respect to the field f is equal to 0 with respect to the field G. Next, let's start with 3, which is a little more complicated, and let's go with the following. Suppose we have any two elements, a, b, and f, and we have a unequal to b. That's the second half of this. Well, let's now suppose the contrary. Let's suppose that phi of a is equal to phi of b. Well, this would then imply that phi of AB is equal to phi of A times phi of B. Oops, excuse me. However, we had it being the case that phi of A is equal to phi of B. So this should be phi of A times phi of A. Now, we'd like to apply cancellation on phi of A to get a, and we'll also say that this is equal to phi of A squared. Let me rephrase what I was going to say. It's not that we'd like to apply cancellation. This equality actually does make sense if phi of A is equal to 0 for all A. And then this equality will always hold. But that will lead us to our first case. That is, this is possible. Otherwise, if we have, if this is not true, then we get phi of AB is equal to phi of A squared, which implies AB is equal to A squared, implies A equals B. However, that's a direct contradiction to our assumption that A does not equal B. Therefore, our supposition is false. Another way of phrasing that is as follows. We can do this proof. We can show that phi of A is equal to 0g for all A and F works. Next, we'll prove that phi of A does not equal phi of B whenever A, B are in F and A does not equal B. To do that, we've shown that that case works and we are not in that case. So, we assume to the contrary, what we assumed here, that phi of A is equal to phi of B. That implies that phi of AB is equal to phi of A times phi of B, which is equal to phi of A times phi of A is equal to phi of A squared. And we cannot have any exceptions due to 0 due to the case we are ignoring. Therefore, we would imply that AB equals A squared, implying A equals B, which is a contradiction. Therefore, this assumption was wrong, and we've shown that phi of A does not equal phi of B for any, whenever A and B are in F and A not equal to B. That's perhaps a better way to go through that proof, so try it again. Try listening again and consider, once you show this case, which clearly works, show that, assume this to the contrary, and show it leads to a contradiction, so this is the only other possibility. Finally, for part 4, we are supposed to show that if phi of A does not equal 0 for some element A and F, then the image is a subfield. Well, first we'll note that if you have phi of A does not equal 0 for some element in A, you are excluding this case. And since we've shown that it's either this case or this other case, then we must be in the other case, that unequal outcomes come from unequal inputs. So we can show that we have a subfield in the following sense. To prove that we have a subfield, we must first show that that we're closed under our operations. Namely, the image of phi is closed under operations of G of addition and multiplication. But we see that if you have any two addition of any two elements in the image, you'll always get another element in the image by applying this rule backwards. And likewise, if you have any two products in the image, a product of any two elements in the image, it is clearly still going to be in the image because you can rewrite it as phi of AB. With that closure done, we should confirm that we have inverses and the 0 element, but that was what proofs 1 and 2 were, namely showing that we can develop inverses and that we can and that we have the 0 element. The way we can do inverses is simply by subbing in 0 to this first equation, and that will give us that 0 minus b is phi of minus b is equal to 0 minus phi of b. So any element in any element in the image of phi has an inverse element. Additionally, we should try to prove this for multiplication, but these are very similar proofs to 1 and 2, and I encourage you to do them for yourselves. Namely, you need to prove that you have multiplicative inverses and that you have preservation of the unity element in the field. Once you do that, you can see that you have a subfield by finally noting that because G is a field and we have subset of the field, then we are going to have preservation of the associativity and commutativity and distributivity of addition and multiplication in the field, since those properties in G hold for all elements of G, and this is simply a subset, so it should hold for them as well. With that, you've proven all the qualities you need to have it as a subfield, and you're done. With that, thank you.